Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the 9th lecture of VLSI Interconnects course. Today we will be simulating RC interconnects. So in this course so far we are towards the end of first module, and in this module we have looked at the resistance capacitance modeling of interconnects. We have seen the distributed RC model and the Elmore delay for that distributed RC interconnect. And in lecture 6 we had seen equivalent circuits. In the previous two lectures we were looking at the effect of scaling on the delay, interconnect delay, and in the last lecture we were discussing ways of mitigating the delay. So now we are well equipped to test what we have studied regarding the RC modeling using simple SPICE simulations. So we will be simulating our interconnect RC interconnect today. We will be doing the circuit modeling of this. So for that I will be specifically using a software which is called LT SPICE. However, there is nothing specific with this software, and if you are comfortable with any other circuit simulator, you are encouraged to do that. There is no issue with the software. If you do not know any simulator, then I can recommend you LT SPICE. This is from Analog Devices. It is freely available for Windows and also for Mac. If you are using Linux, then you can install this LT SPICE using Wine. So I have tested this software on Linux as well. Other than this, if you do not want to install anything on your system, if you have limited computational resources, this is anyways a lightweight software, but still if you have some restriction on installing something, there are multiple online simulators as well. One of them is Multisim. So here you can go to sign up, create a login for free, and with free login also, a free account also, you can simulate simple circuits. The only issue with free account here is that there would be limitations on the number of elements that you can use in your simulation. So if you want to say simulate an interconnect which is you segment the interconnect in say 10 segments or say 20, then it might be an issue. But other than that, you can test all the basic things with this software simulator as well. Again, as I said, there is nothing specific with the simulator, but I will be using LT SPICE. So the agenda for today is the following. We will be comparing lumped RC interconnect model and a distributed RC interconnect model. We will be looking at the pi equivalent models which we had studied earlier, and we will compare the performance of these pi equivalent models with distributed RC models. And towards the end we will also be simulating branched interconnects using these pi equivalent models. So let us get started. So here in this exercise I am giving you few problems to solve work on. So it is given to you that there is an RC interconnect and it has the following parameters. Length is given 1 mm, resistance per unit length is given, capacitance per unit length is given to you. Now you want to simulate this interconnect under different scenarios. So for that, for a single interconnect, there are multiple sub parts here. So in the first part we will be simulating this interconnect using a lumped RC model, and we will see like does this simulated RC model gives you like 63% delay, does it match with the theoretically calculated value for the lumped model. Then we will simulate the interconnect by dividing it in 5 segments and then in 10 sections, and then in part D we will be simulating the same interconnect with pi equivalent model and pi 2 equivalent model and compare the performance with a distributed model. Then in question 2, one interconnect tree is given to you, branch interconnect like this. So this is your input, and these are your output. So, this is say V out 2 and V out 5 and V out 4, and for this you have to simulate this interconnect. Lengths are given to you L1 and L2, and you can simulate this. So, if you are already familiar with any circuit simulator, even before going through this video, you may pause this video with these values which are given here, and then you can start simulating. Start simulating and comparing it with our theory that we have seen. Towards the end, I will give you one more exercise which I will not be explicitly solving. So, in this you have to repeat exercise 1 and 2 when there is some source resistance and load capacitance. So, this would be the agenda for today. Right. So, let us get started with the first case. So, you have an RC interconnect. The following parameters are given to you. The length is 1 mm. So, length here is 1000 micrometer, that is given to you. Your resistance per unit length R is also given to you. So, your R is 0.02 ohm per micrometer, and your capacitance is 0.5 femtofarad per micrometer. We want to now simulate this. So, for simulation, what we are interested in is we will be giving a clock signal like this to the input. So, to the input we will be giving a pulse signal like this, and then for this case we will be investigating the output V out of t here. So, we will see if there is any delay in this output response. So, this is what we will be investigating. Right. So, for that we need to consider some clock frequency also. So, typical value is given to you, I mean for understanding this. So, let us consider an input voltage of clock 2 gigahertz. However, you can take any other value also, as long as your time period is larger and comparable to RC delay, that you can observe the delay, also the delay is not more than your time period. Right. So, peak voltage is 1 volts and 50% duty cycle. For this you have to simulate it. So, let us now go to the simulator and let me construct a simple first circuit, and then later on we will proceed. So, this is the window for your LT Spice. If I create a new schematic, I get something like this. So, okay, let me create a new schematic, and for this I can now see that there is a blank space. Here I can add different components. So, either I can click from here, I go to this, I select voltage source. So, I want a voltage source here, I will select a voltage source and drop it somewhere. Then I want a resistor. So, I can go here, I click, I can include the resistance from here. There are also short keys here. So, I can use that also. So, I have a resistor, I can rotate it, I place a resistor here. Then I require a capacitor. So, I include a capacitor here. So, in this video I am using short keys from keyboard, hotkeys from keyboard. If you are not familiar with that, you can also always include all of these from this menu. So, now you have voltage source, resistance and capacitance. If I go to the lumped model, what will be my interconnect resistance? My interconnect resistance R L would be R into L, and if I substitute these values here of 0.2 ohm per micrometer multiplied by 1000 micrometer, I will get 20 ohms. For interconnect capacitance also I can do the same thing, and if I substitute this value here, so this is 0.5 femtofarad, I multiply that by 1000, so I get 0.5 picofarad. So, I have to now include these values in here, right. So, let me give the values. So, the resistance here can be entered as the value was 20 ohms. So, let me enter 20 ohm here. Then I also have to include capacitance. So, that was 0.5 pico. So, that is also included here. Then I have to connect the circuit as well, right. So, I can go here, there is this wire option. I can connect the circuit like this. Then there is ground plane. I also need to connect the ground plane. Voltage is defined with respect to that. So, I take the ground plane. I am taking two ground planes, so that I can just then connect these two together. So, this is connected here. I can also do something like this, that I take this capacitance and connect it to the same ground, but I am using this two grounds to connect it. So, once I have done that, I now have to let me also label this resistance. So, let me label this as R interconnect, and let me label this as C interconnect. I need to set my voltage. So, if I right click on this voltage source, I get a window like this, where it asks me for some DC value, but in this case we do not want a DC value, we want a clock signal. So, we go to advance. I am showing this again. I right click there, go to advance, then I select pulse. Initial value of the pulse voltage I have set as 0, final V on I set as 1. I am also including a delay, because it is easier to delay in the starting point of your pulse, because then it becomes easier to compare the different rise times and delays for different circuits. This T rise you should keep as small as possible. We want an ideal pulse. Similarly, for T fall, let us keep it as small as possible. Now, what about T on and the time period? So, T on and time period will be decided by the frequency that you have. So, for this you have a frequency of 2 gigahertz. So, your time period will be 1 by 2 into 10 to the power 9 or 0.5 nanoseconds, and then your T on would be half of that, if we consider 50% duty cycle. So, this is 0.25 nanoseconds. So, we then enter these values in here. So, T on, let us keep it as 0.25 nano, even though I mean if you take some slightly different values, your analysis will not change, especially in this case. So, we get all these values, we click OK. We also want to label, I mean it is a good practice to also label your key points where you want to look at the voltages. So, let me create a label for this point. So, this is V in, and then this is V out. Let me change the thing. So, this is my V out, and then I am all set to simulate it. When I simulate it for the first time, it will ask me the stop time. So, maybe I can put it as 0.5 nanoseconds as well. Yeah. So, this is my circuit. Now, if I simulate it, I get this. Now, if I bring this cursor near any of these wires, I get this symbol like of a multimeter probe. So, when I click it, this is my input and this is my output. Now, let me bring it, this one here and this one down. So, here if I now zoom in, I want delay, right. So, I can see that this is my input and this is my output, and if I on the output, if I click for a cursor, I can drag it, I can create two cursors. so that this comes to the starting point, and then this one is the delay. I mean the difference would be your delay. So, if I bring this to so this is like the second cursor I am moving, my vertical is, if I bring it to 0.63, close to 0.63, I can see that my cursor 2 minus cursor 1 comes out to be around 10 picoseconds. Right. So, this is not very exactly spaced because this is computed discrete points, but you can see this comes out to be this around 10 picoseconds. Now, let us see for the lump model, do we get that. So, if we see this, your delay, your RC delay would be R interconnect into L interconnect, and if you multiply these two, you will be getting 10 picoseconds. So, that is what you are getting. So, once you have tested this, it is, before going to any distributed model, it is highly recommended that you test this, because that will ensure that your clock and your parameters and your circuit is correctly simulating. Once you have done that, now we are all set to simulate the distributed model. So, now in distributed model, what we are going to do is that we will segment this interconnect in 5 sections. So, we will have say 1, 2, 3, 4 and then 5, even though they are not drawn equally, consider they are equal. So, all of these are equal and each of them has a separation of length of delta x. Right. So, I have divided this the entire length into 5 segments now. So, for each of these 5 segment, what I have is R1 C1 like this. We have seen this type of distributed model earlier also. In this case, my R1 is R into delta x and C1 is C into delta x. In this case, delta x is not going to 0. So, it is not an infinitesimal section. What is delta x? Your delta x is equal to L by n, n in this case is equal to 5. So, if then I substitute this, my R1 comes out to be 4 ohms, basically the interconnect resistance divided by 5. Earlier it was 20 ohms, so this comes out, individual value comes out to be 4 ohm each, and then the individual capacitance C1, that comes out to be 0.1 picofarad. So, earlier it was 0.5 picofarad. So, this comes out to be 0.1 picofarad. Now, if you want to simulate this, what you would be doing is you can go to this, either create a new file or you can go here, change the value here to say 4 and then this to 0.5 sorry 0.1. This I can maybe number say V1 or something intermediate, and this I can number it as say R, label it as R1 and this as C1, and then what I can do is I can go and copy this circuit and then place it, then again I zoom out, then I copy this and then again paste it, and then I can repeat this. So, R1, R2, R3, 1, 2, 3, 4 and one more is this, and then I can connect these. Right, and then final one I can name it as V out. Other things can remain same, then let us see if this runs. So, if I do the simulation again, I can get the input and then the output like this, right, and then from here we can see what is your delay for the distributed model. So, again let me create two cursors. So, first cursor is at the starting point and the second one is here 0.63, close to 0.63. So, yeah, so if I look at this, I can see I can get the difference between them, right. So, what I have done is that I have gone ahead and created this type of circuit. So, let me then show you the comparison. So, now what we want to do is that we have computed this. Similarly, what you can do is you can create your 10 segment circuit. So, in that case your R2 will be RL and RL divided by n is 5 in this case. So, n is 10, in this case n is equal to 10, and then if you substitute the values you will get something like this. Now, what you have to do is you have to see that when you divide this into large number of segments, does this 63% delay converge to the Elmore delay in case of large number of segments. So, what was your Elmore delay? If we look at the theoretical value of Elmore delay, we were getting the Elmore delay as RC L square by 2. If I substitute these values, I will be getting a value of Elmore delay as 5 picoseconds. So, let us check whether we get it. So, let me close this one and then so I have already created this interconnect segments. So, either when you want to compare these things, there are either you can create different circuits, different files, or you can create all these circuits in the same file as well. So, what you have is C lumped here, this is R lumped, this is the lumped component and these are the distributed components. So, for this okay, I have not labeled it here. So, let me create a label. So, this is V lumped. So, let me place a V lumped here. So, now let me run it. This is my input, this is my lumped delay, this is with RC interconnect with 5 segments, I can see this, and the third graph which will be here is my RC delay with 10 segments. So, here we can see that as we had predicted in theory that for a distributed model my delay is approximately half of my lumped model. So, if I zoom into this region, let us check that whether we are getting that or not. So, for lumped model, yeah, so we are on this right curve, and for this here I am for lumped model I am getting this values here as 16. So, remember my starting value was close to 10, right. So, my starting value was 10 and my second cursor is so my second cursor is 0.637, yeah. So, here I am getting something around 6 picoseconds. Theoretically, I should be getting 5 picoseconds. If I now check it for 10 segments, for 10 segments, let me close this. So, for 10 segments I can see that this is coming as 0.59, around 0.59. So, with 10 segments we can verify that your delay is now closer to your Elmore delay. Right. So, now let us check the pi equivalent model. So, if what we have seen here is that if I have very large number of elements. So, for example, for this single wire I require 10 segments to represent it faithfully as a distributed model. If I had a circuit and if I wanted to replace those wires and incorporate the effect of those wires into my entire circuit simulation for that single wire, I would have to replace it by say 5 or 10 segments, but at least say 5 segments. That would have been so these would have been 10 components. Here you would have 20 components, right. So, what we will then do is we will look at the pi equivalent model, and this pi equivalent model we replace this interconnect by just a pi equivalent model with less number of components. That was one of our motivations, right, for studying pi equivalent model. So, here there is a pi equivalent model and this one is pi 2 equivalent model. How we get these values we have already seen. So, your resistance in pi equivalent model is replaced by a single element, single R L. In case of pi 2 element, your resistance is represented by 2 elements and your capacitance is represented by 3 elements. Basically, you break this down into 2 and then we have seen how we get C L by 4 and C L by 4 and C L by 2 in here. So, if we substitute those values for R L and C L which we had computed earlier, these values, your R L and C L values, from that we can easily get the values that are here, right. So, we can easily get these values. What you have to do is you have to simulate this, make this in your simulator and then check does the pi equivalent model give a better approximation of the distributed model with lesser number of terms. This is something that you have to check. So, you can pause the video and then go ahead and check this on your own. However, I will be I have already made the circuit. So, I will just be showing you that. So, if you can make a circuit like this where there is a pi equivalent model and then there are pi 2 equivalent model and a distributed model with 10 segments. Now, for this if I simulate it, I will be getting V in like this my V in green curve, then this is my pi equivalent model, this is my pi 2 equivalent model. In pi equivalent model I just have 3 terms, in pi 2 equivalent model I have 5 terms, in here I have 20 terms. So, let us see my distributed model. So, the third curve here is the pi sorry, the third curve is the distributed model. Let me zoom in and see this. So, yeah, so if I zoom in I can see that all the 3 curves are very close. In fact, if I want to check my pi 2 model, so for example, if I check the pi 2 model and the 63% delay in that, so now here if I look at this, this value is 5.052, which is much closer to your theoretical value of Elmore delay of 5 picoseconds than this curve. So, if I want to say check this curve, then this will be so this will come out to be 0.58 or something like that, 58 picoseconds, something around that, 5.58 picoseconds, right. So, we can see that with less number of elements we can simulate or represent your interconnect and closely get the distributed response for your interconnect, right. However, at this point I want to emphasize something very important. So, in this analysis what we were saying was that, I mean, we were looking at 63% delay and then matching that with the definition of Elmore delay. However, I would like to emphasize here that by definition Elmore delay does not mean 63% delay. It is just that in the case of RC ladder circuits, this delay comes out to be close to 63% delay, because this is basically the dominant RC delay. You ignore all the higher powers of S in the denominator of your transfer function, and whatever is the dominant, that is 63%. This is a specific case. For example, if you had a circuit output voltage like this, in that case if this was say linear, in that case your slope would have, this is your slope. So, slope would have been constant here, like constant, and in that case you would have got something like this. So, this would have been somewhere like 0.5, 0.5. So, this would have been your Elmore delay T d would have been equivalent to say 50%. So, it depends on your waveform. In the case of RC circuits, it comes out to be the same. Now, let us take this, we have this final case where there is a RC interconnect tree like this. We have already seen that how we can represent this with an equivalent circuit like this. So, we replace each segment by an RC term and then club the RC pi network and then club the capacitances. So, you will get something like this. You can calculate the values, and then so these values are also mentioned here. This is for L1 is 2 mm and L2 is 1 mm. Here now the delay is going to be more, so you may have to change or increase the clock period. So, here if I then compute the Elmore delay between say 0.1 and 2, so or input and output at 0.2. So, your delay T d 2 would be something like this, and then T d 5 would be coming out to be something like this, right. So, again you can construct this structure in your simulator, and then when you construct it, it will look something like this. This is your input, these are your outputs, 3 outputs. If you simulate it, you can then compare the output. So, this would be the second output and this is the third output. So, here you can see, I mean, with this branching and this, now your delay is almost comparable to your T on time. Let me zoom in, and then if you zoom in again, you can repeat the same process and then compare your delay. In this case, you will find that especially for the case of I mean V out 2, your shape is different, and therefore, your Elmore delay would be somewhere, I mean this 60% delay would be something shifted below the theoretical value. So, you can check this out for say V out 2, and also for, if you want to check it for V out 5, you can check it for V out 5 as well, right. So, these are the theoretical values, you can check, compare with that, right. So, I will end this by giving you an exercise. So, you have to repeat exercise 1 and 2 with considering these resistors. So, there is a source resistor R d of 20 ohm and a load capacitance C L, this is C L, of 500 femtofarad, and then you have to connect this C L here as well, and C L here as well, and also in for a single interconnect, and then you can repeat this. You may have to change the clock frequency to make the time period appropriate, right. So, let us summarize what we have seen. So, in this lecture we saw the simulation of RC interconnects. We compared lumped model, distributed model and pi equivalent models. This is the final lecture of this module on RC interconnect modeling. We have covered almost all aspects of an RC interconnect modeling. In the next lecture, we will be starting with the second module, which is on resistance, inductance and capacitance interconnect modeling. In the next lecture specifically, we will be discussing why this inductance comes into picture, and we will see that why it is important at high frequencies to consider this inductance. That is all for today. We will meet in the next lecture. Good day.